Red right here is the Bode diagram. The green is the step up from the step function, and the blue is the step down from the step function. And as you can see between the gain, the step up was quite a bit different. As far as the step down in the Bode diagram, pretty similar results. Dead time was significantly different with the step up, but again, pretty consistent with the step up, or step down in Bode, as well as the time constant. For the middle range, it's a little bit, not quite as much variability, but still the step up is larger than the Bode and the step down with all the parameters. And with the higher range, it's kind of a little bit even more closer with all of them. But here's the feedback control loop. The power goes in. The controller gains, but sends the message to the transfer function, which manipulates the variable, and it goes as output. However, if you want a certain output, this controller gain will send it back through here and tell it whether to go higher or lower, whether to increase or decrease the input within the system. This gives us a closed loop transfer function, which is numerator would just be the straight voltage, or straight going straight through the system. The denominator would be 1 plus 0 loop around, since there's nothing on the bottom. It's just the same as the numerator. But we plotted that up to root locus plots. This axis would be the real axis, and this is the imaginary axis, being that at these points the roots are imaginary. It gave us a critical damping right here, 500 dampening, 10th dampening, quarter, or 500 decay, 10th decay, quarter decay in the ultimate point, being where this is where there's it's relatively monotonic, and after the ultimate controller gain, the oscillation never really dies down and never really stops fluctuating. But as far as the parameters of that go, the controller gain, the ultimate was much higher with lower frequencies apart from the middle of the upper. Same with quarter decay, 10th decay, 500 decay. It's pretty consistent as far as critical damage. Or no, it's another order of magnitude higher with that as well. So. But as far as the actual proportional controller design goes, you can have a system that's monotonic or a little bit more oscillatory. But the main part about it is you will always have an offset. This is a monotonic relationship right here. It's the output right here, the set point. It's trying to tell it to jump up to 30 volts right here. Go with a monotonic response. It's just kind of flat, just kind of curves up, never really oscillates or anything like that. And as you can see, you have a pretty large offset right there. That's with a controller gain of 0.1% per volt. And as you raise that number a little bit, it starts to oscillate. There's less of an offset with this oscillation, however, but the oscillation eventually dies down. So that's oscillation with the decay. Then you can also have oscillation that never really dies down. This offset, if you took an average, is a little bit closer than offset with decay. However, having a system that never really dies down can have negative effects. This is the as different controller gain values are inserted into lower values. This offset goes from 1 and slowly increases as that controller gain gets lower. Same with middle values. See this. and then also with the higher values right here. And you can see oscillates until it gets to a certain point, and then it just becomes monotonic as the value gets smaller. But as far as actually applying that design to the system, once it's actually applied, you start out by not specifying a controller gain and seeing where the output takes you. And then you apply the different values of the controller gain to the design and figure out the different responses within the actual system. And you still always have offset with the system. So we started out by not specifying controller gain. I went up to about 68 volts. Just kind of jumped up there. I never really had that step. And you can have kind of monotonic response where it just kind of jumps up like that. That's with the lower values right there. There's also the oscillation with the decay. This is the step down. Just trying to jump down to this point right here. This is the input jump. And as you can see, there's still this offset. The oscillation slowly dies down. And this is the input right here of the system that also oscillates in the same manner. And finally, there's the oscillation with no decay. As a step up happens, it just continues to oscillate with the system. There's still an offset with that, although not quite as large. And with this lower range, you can see it's the same offset type of thing. I'll compare these results with the other one here shortly. With the middle range and with the upper range. As far as the low values of this is the design versus when it's actually applied. So the low values right here, the actual offset, and the offset for the design is a little bit higher than the actual applied. It's not twice as high in most instances. About the same as far as our critical damping, 500 decay, 10 decay, quarter decay, ultimate controller gain. And what's interesting was with the higher values, the actual application values are higher than the design criteria, which is kind of interesting about the system. Then these new parameters were plugged into the bootleg to define the same parameters using TL's 3.33 with 2.0. And this is the portion of controller's root locus right here. Again, this 0 is the ultimate controller gain. This is quarter decay, 10 decay, 500 decay, critical damping. This being the imaginary, or the real roots right here, the imaginary roots right here. And as far as the parameters go, when the tau L is multiplied by 4 divided by 4, the parameters stayed pretty consistent throughout the whole system. No range, similar results were given. And with the upper range as well. But overall, we determined voltage is a very complex system, very hard to control and all that. But despite all this complexities, we determined it can be controlled. But the difficult question we're still looming overhead: will we be able to design a control system that can control all three ranges, the middle, the higher, the lower, despite all the different parameters within the system? So, any questions?